Okay, so let's continue your notes for gas laws. So open your books to page 184 and try question number 3. Pause the video, and then when you're ready, hit play to see how to solve it. So you should have started out by making the chart. Make sure that you're labeling your variables P1, V1, P2, V2. Make sure that you have units for each thing. And remember, what I'd like you to do is to predict which or what is going to happen. So you should have noticed here that volume is going down. That temperature is staying constant. And so if the volume goes down, remember that's the size of the room, but temperature stays constant, so gas particles are moving at the same speed, what should happen to pressure? So one more time. We are the gas particles. The room is getting smaller, but we are moving at the same speed as we walk through the room. So what should happen to pressure? You should predict that pressure is going to go up. So whatever you get as your answer for P2, it should be greater than what you would get for P1. So when you solve this, you should get an answer that is greater than 69.0 millimeters of mercury. So remember, this is the formula that you should have used. When you sub in, make sure you include units, and then remember to make sure that you are rounding to the correct number of sig figs. Yesterday, you copied a list of conversion factors for pressure units. So let's practice converting. So pause the video again, convert 1790 millimeters of mercury to atmospheres. When you're finished, click play and see if you match what I did. So remember, you should be using dimensional analysis. So the units that you want to cancel need to be on the top and the bottom. Units that you want to get need to be on the top. And then just watch your sig figs when you are solving. So 2.36 atmospheres should be your final answer. So let's try another one of these where we talk about how the factors affect a gas. We did 2 of these yesterday. This one's going to sound a lot like the ones we've done, but a little bit different. So here we go. A closed container containing a gas. The container has a piston. Pressure is constant. So remember, that is gas particles hitting the walls of the container. Volume decreases. So this is the size of the room is going to change. So here are the pictures that you should have. Remember, this is the piston, and it can decrease or increase your volume. In this case, it's decreasing it. It's making my volume smaller. Remember that the blue X's are my gas particles. So what factor have we not talked about here? We have pressure, we have volume, we have the same number of X's, so amount is staying the same. So you should recognize temperature is the factor that we are going to be changing here. So make sure that you're copying this down. If pressure is constant and volume decreases, then temperature also decreases. And so what kind of relationship is it if one thing decreases and then the other thing decreases also? Or vice versa, if this one increases, then this one increases. So you should tell me that's a direct relationship, and this is called Charles's law. Okay, so let's try another one. So open to page 182 and let's look at number 2. If a sample of gas occupies, and let's add a decimal point to this so that we have 3 sig figs, 100 centimeters cubed at 200.0 Kelvin, what volume would it occupy at 150.0 Kelvin? So remember, you need your chart, you need to predict, you need formula, you need to solve. So pause the video, follow the steps. When you think you're done, hit play and see how you did. So here's the chart that you should have created. You should have noticed that temperature went down, which means that the particles are going to move slower. But pressure's constant, so that means that they're still going to hit the walls the same amount. So how can we move slower but hit the walls of the container the same amount? Hopefully you recognize that that would mean that volume, the size of the room or the size of the container, would have to get smaller. So V2 should be smaller than V1. And then you used this formula. And then you substituted and solved. And yes, V2 is less than 100 centimeters cubed, so you are good. All right, let's try one more. Again, pause the video, solve it, and then hit play to check. Okay, so here's the chart that you should have made. V1, T1, V2, T2, and then recognize that P is constant since the problem doesn't talk about it. Make sure that you remember when you're using these formulas, temperature has to be in Kelvin. So you need to add 273 to both of those temperatures before you start subbing into formulas. So hopefully you're recognizing T1 is greater than T2. So that means temperature decreased. It went from 293 to 273. And pressure is constant. So what would you predict is going to happen to V? So temperature is going down, I'm moving slower, but I'm still supposed to hit the walls the same amount. So my container needs to be smaller. There's your formula. There's your substitution. And there's your answer. And 466 milliliters is less than 500, so my prediction is correct. All right, another scenario. How do factors affect gases? This time we're going to have a closed container containing a gas, and we're going to increase the temperature. So I'm going to draw my containers without a piston, because volume is constant, so volume's not changing. Same number of X's, same number of gas particles in each container, but one of them I'm going to heat up. So you see my Bunsen burner. So volume is constant, but temperature is going to go up. So what does it mean if temperature goes up? So remember, that is the energy of the gas particles. So if they have more temperature, they have more energy, so therefore they move faster. If particles are moving faster, what does that mean about hitting the walls of the container? You should tell me that it's going to hit the walls more. And so what does that mean about pressure? You should be able to tell me that that would increase pressure. If volume is constant and temperature increases, then pressure increases. So it's one of these again where if this one increases, this one also increases. What do you call that kind of relationship? And this is a direct relationship. This is Gay-Lussac's law. So Gay-Lussac's law says that if temperature goes up, pressure goes up, assuming that volume is constant. So here's your formula that you're going to need to know for this one. Remember, when you're using these, temperature has to be in Kelvin, and pressure can be in any units, but it has to be the same unit. So P1 could be in atmospheres, P2 is going to have to be in atmospheres. If P1 is in torr, then P2 has to be in torr. So whatever the units are, they just have to be the same. Okay, so for your classwork, I want to see the problems that you worked today in your notes. So snippet those, turn those in on eBackpack. After you do that, and your classwork is due before the end of the class period, then you're going to start working on homework. So check your homework calendar for homework that's due. I will be here tomorrow for tutorials if you need me. I will not be here Wednesday afternoon for tutorials.